When World War II began, Britain's primary anti-tank weapon was the 40mm 2-pounder. It proved effective against the early models of German light and medium tanks. However, in North Africa, German forces began to add extra armor screens to their tanks. These additional protections, however, were often ineffective and prone to falling off. Soon, newer German medium tanks began to feature 2-inch front armor. The 40mm gun could only penetrate these enhanced vehicles at very close range. By the summer of 1941, it became clear that Britain required more powerful tank guns. American Lee and Grant tanks, equipped with their 75mm guns, provided a temporary solution. This, however, was merely a stopgap measure. British forces were anticipating the arrival of their own 57mm 6-pounder and 76mm 17-pounder guns. While the 6-pounder fit into British tanks, the significantly more powerful 17-pounder proved too large for existing tank turrets. German tanks continued to grow in strength. Soon, Britain encountered the formidable Tiger heavy tank. Studies of destroyed enemy tanks indicated that guns approximately 3 inches in caliber were most effective against Tigers. The Americans already possessed such a weapon. Their 76mm gun, mounted on a self-propelled tank destroyer, demonstrated the ability to destroy Tigers. Britain's 3-inch caliber guns, such as the 17-pounder, were potent, but could only be towed. This inherently made them vulnerable. For instance, on June 2, 1943, a 17-pounder gun successfully knocked out 6 enemy tanks, including 2 Tigers with 6 shots. However, the final enemy tank managed to return fire and destroy the gun. Designing a tank turret for the large 17-pounder proved challenging. Consequently, British engineers devised a simpler method to transport the gun. They welded a truck hook onto a tank, effectively converting the tank into a tow vehicle. This, however, was far from an ideal solution. There was no dedicated space on the tank for the gun crew or their ammunition. Gunners were forced to sit on the engine compartment roof, cradling ammunition boxes. This severely limited the amount of ammunition they could transport. Further problems quickly emerged. The truck hook proved weak and was easily damaged when mounted on a tank. It was also positioned too low. If the tank traversed a bump, the gun could strike the ground and sustain damage. The hook could not be welded higher as it would obstruct access to the tank's engine. Even on tanks where engine access was not a concern, the towed 17-pounder would dip sharply when traversing rough terrain, risking damage to its barrel. There was consideration for utilizing a different towing component from the 25-pounder gun. However, this would still necessitate major modifications for the larger 17-pounder shells and would not resolve all existing issues. Despite all these inherent problems, the Tank Design Department approved this towing hook on May 7, 1943, with plans to order 5,000 sets. Simultaneously, a more promising solution was under development. On June 8, 1942, Canada inquired about mounting the 17-pounder gun onto a tank. They were informed that designs would be ready within 2 months. Even at this preliminary stage, the gun was already envisioned for the Sherman tank. On June 9th, General Andrew McNaughton learned that future Canadian Shermans might be ordered with the 17-pounder instead of the usual 75mm gun, a decision which went against American requirements. By July 25th, such tanks were assigned names: Buffalo II for the Canadian version and Bear II for the standard medium tank. The Buffalo II was later renamed Grizzly, but the Bear II was never ultimately constructed. The British Army planned to equip 30% of its tanks with this new gun, 60% with regular 75mm guns, and 10% with 95mm howitzers for infantry support. British military leaders initially considered using their own domestic tank designs. By the spring of 1943, they had 2 primary options: the heavy Tog tank and a tank destroyer, which was later named the Challenger. However, work on the Tog tank had already ceased, as it was clear this large and clumsy vehicle was outdated. The tank destroyer appeared more promising, but by the fall of 1943, it too proved not to be the optimal choice. Already receiving GMC M10 tank destroyers, well suited for powerful anti-tank guns, the British made a pivotal decision: to mount their formidable 17-pounder gun onto these vehicles, replacing the less powerful American 76mm weapon. Shortly thereafter, a similar transformation was planned for the M4A4 medium tank. known to the British as the Sherman 5. Development commenced in August of 1943, running concurrently with the M10 project. This simultaneous effort frequently led to confusion between the two distinct projects in internal documentation. By December 3, 1943, most of the designs were finalized, with the exception of the critical ammunition storage plans, which were anticipated by the month's end. Nevertheless, the decision was made to begin converting the tanks in early December. Concerns arose among designers about the turret becoming excessively heavy. To address this, they opted for rigorous testing with added weight. Approximately 1,680 pounds were attached to both the front and back of the turret for these trials. 2 M4A4 tanks underwent testing, one equipped with an oil gear system for turret traverse, and the other featuring a Westinghouse system. Each tank traversed over 1,000 miles, both on roads and off-road, without engaging the travel lock, all while continuously turning the turret. Both systems unfortunately failed during these demanding tests. However, a subsequent investigation revealed that their fundamental designs were not to blame. The oil gear system failed due to a metal defect, while the Westinghouse system's failure was attributed to incorrect assembly. The conclusion was reached that both systems were indeed suitable for the 17-pounder tank, especially given that the new gun added less than 1 ton to the turret's overall weight. This decision was later revised, with only tanks equipped with the oil gear mechanism ultimately deemed suitable for the new gun. To accommodate the new, heavier gun, a completely new cradle, mantlet, and fixed armor were meticulously designed. A new elevation mechanism became essential, and the tank was fitted with a telescopic sight, Model 52, offering 3 times magnification. To manage the formidable recoil, 2 recoil brakes sourced from a 6-pounder gun were integrated. However, this proved insufficient. The gun's extended recoil sweep physically prevented the radio from being placed in the turret's rear. The British ingeniously solved this by excising the turret's rear wall and adding an armored box specifically for the radio. This armored box ingeniously doubled as a crucial counterweight. Its sidewalls were 2 inches, or 50 millimeters, thick. The roof and floor were 1 inch, or 25 millimeters, and the rear wall measured 2.5 inches, or 64 millimeters. Other significant turret modifications included 3 exhaust fans integrated into the roof, the addition of a separate loader's hatch, and a mount for rangefinder Model 12 on the commander's cupola. The tank was designed to carry 78 main gun rounds. 59 of these were stored beneath the movable floor of the fighting compartment, 40 on the right side and 19 on the left. A section of the floor was cut out to provide access to this ammunition. 5 rounds were kept immediately ready for firing, 3 positioned beneath the elevation mechanism, and 2 in a dedicated rack directly in front of the loader. The assistant driver and his machine gun were removed from the design. The resulting opening was welded shut, creating space for 14 additional rounds. Ammunition racks located above the fighting compartment floor received supplementary armor, specifically to reduce the risk of explosion should the tank sustain a hit. The tank also carried 20 boxes of 7.62 millimeter coaxial machine gun ammunition, 6 cases of 12.7 millimeter anti-aircraft machine gun ammunition, and 27 charges for the 2-inch smoke mortar. In the final design iteration, the main gun ammunition load was marginally reduced to 77 rounds, with 1 round removed from its position under the left floor. Loading ammunition proved challenging due to the tightly fitting box lids. Even a skilled 4-person crew required 18 to 22 minutes to fully load the tank. Firing tests commenced on December 30, 1943. The tank fired 100 rounds with the turret oriented forward, backward, and 90 degrees to both the left and right. This comprehensive testing evaluated the tank's inherent stability and the integrity of the gun's installation. Crucially, during these initial trials, the hatches remained open, the engine was off, and the crew positioned themselves outside the vehicle. The first 96 shots proceeded without any serious issues. The tank demonstrated itself to be an excellent, stable platform for the powerful gun. Any rocking motion quickly dissipated. The only minor issues encountered were 1 instance of short recoil after 42 rounds fired in 30 minutes, and the presence of some residual burning gas within the barrel. Significantly, no flames were observed entering the turret. However, the situation shifted significantly when the hatches were closed prior to the 97th shot. Even with the engine operating at 1,500 revolutions per minute, sufficient gas accumulated within the turret to cause flames to blow back inside. An external flash was visible through the 6-inch radio opening. Following the 98th and 100th shots, ignition was clearly observed. Gases contained within the spent shell casings, which landed upright on the floor, continued to burn for several seconds longer than the gases inside the main compartment. A deliberate pause before the 99th shot allowed the barrel to cool, successfully preventing ignition on that occasion. Flame returning from the gun, a phenomenon referred to as blowbacks, was anticipated following earlier tests conducted with the Challenger tank's 17-pounder gun. Nevertheless, this issue remained a serious concern. Engineers implemented a temporary fix by deactivating the gun's semi-automatic system and restricting its rate of fire, pending the discovery of a more permanent solution. Despite these challenges, the installation of the new gun was largely considered a success. The gun's components sustained no damage after repeated firing, and the turret maintained its ability to traverse easily by hand. Further testing in January and February 1944 brought to light numerous new issues. The semi-automatic system frequently malfunctioned, unpredictably closing the gun's breech after spent shell casings had been extracted. The main scope proved unusable in rainy conditions, compelling the commander to repeatedly dismount to clean the periscope. During one particular test, the gun's safety system failed entirely, halting both mechanical and electrical firing. Recourse was had to a sledgehammer to discharge the weapon. Additionally, the problems with burning gases or blowbacks remained persistent. All these accumulated issues significantly hampered the gun's rate of fire. Even with readily available shells, the weapon could only achieve 5 to 6 shots per minute. Subsequently, the loader required 1.5 to 2 minutes to prepare additional shells. This particular delay was not considered a major impediment, as the tank would likely be maneuvering during that reload period. The British were acutely aware that the gun's muzzle flash would invariably betray the tank's position. Furthermore, the muzzle brake itself proved excessively heavy, complicating the elevation and depression of the barrel. Subsequent firing tests indicated that blowbacks occurred infrequently inside the tank when high explosive shells were being fired. Moreover, these blowbacks caused negligible harm to the crew, resulting only in the slight singeing of a distracted loader's arm hair. Various methods were attempted to clear smoke from the tank, including the innovative use of compressed air within the barrel. Ultimately, the tank was deemed ready for combat after a protective screen was installed for the commander, intended to block the flashes. Nevertheless, testing with an additional exhaust fan persisted until March 20th. This particular fan was subsequently identified as the most effective method for preventing blowbacks. In March, reliability trials for the tank were also conducted, with particular attention paid to the behavior of the shell racks while the vehicle was in motion. On March 23rd, following a journey of 585 miles on roads and 372 miles off-road, testers uncovered significant problems. Access to the clutch and brake adjustments was obstructed by the shell racks. The racks themselves also required modification because they inflicted damage upon shells during periods of vibration. The final series of tests on the actual production tanks commenced in April. The weighing of tank T2281715 revealed that the converted vehicle was exceptionally heavy, registering at 76,650 pounds. This additional weight primarily impacted the rubber components of the road wheels, which already constituted a known vulnerability of M4 tanks. Consequently, a decision was made to restrict the tank's speed to 15 miles per hour when undertaking long-distance movements. To facilitate easier access to the brakes and clutch, apertures were precisely cut into the shell racks. The racks were additionally outfitted with spring latches, and the original felt pads were replaced with leather ones, streamlining the process of shell removal. It was discovered that the turret's turning gearbox was operating under an excessive load. However, a more robust version was already undergoing trials. Tests also confirmed that carbon monoxide levels inside the tank, even with the engine running and the gun firing, consistently remained below the safe limit of 0.05%. During its trials, the tank embarked on a journey of 1,716 miles. Its turret intentionally unlocked to thoroughly test the rotation system. The results were positive. The turret proved capable of turning smoothly, even when the tank was tilted up to 15 degrees. However, a subsequent inspection revealed a significant accumulation of dirt within the turret ring. While this did not immediately impede the mechanism's function, it posed a potential long-term risk of rust. Elsewhere, the radio's placement presented a challenge. Due to the tank's unusually long gun, the turret had to be positioned backward during travel. This design choice meant the radio housing hung directly over the driver's head. A raised driver's seat therefore carried the risk of the driver striking his head on uneven terrain. Furthermore, even the improved ammunition racks were found to damage shell casings during movement. Yet, despite these minor drawbacks, the tank ultimately performed well in its mobility tests. No entirely new issues emerged, and the Sherman 5C demonstrated a reliability comparable to the original Sherman 5 model. However, the subsequent field trials uncovered more serious problems. When benchmarked against standard Sherman 5 tanks, tire failures for road wheels dramatically increased by 120%. Even more concerning, suspension spring failures soared by an astonishing 440%. Military experts concluded that the tank's significant weight, 38.25 tons, represented the absolute limit for its suspension system. The final drives, too, were operating under maximum strain. On May 15th, the tank underwent comparative testing against a German 7.5-centimeter PaK-40 gun. Though marketed as flashless, the German weapons powder still produced a muzzle flash, albeit one significantly less noticeable than that of its British counterpart. The British 17-pounder, when fired, also generated large volumes of brownish-yellow smoke. This smoke was clearly visible against the sky, but tended to blend in with the ground. In stark contrast, the PaK-40's white smoke proved far easier to spot. By February of 1944, the supply of Sherman 5 tanks suitable for conversion began to dwindle, largely due to the cessation of M4A4 production in the United States. As the military scrambled to find alternative tanks, the fighting vehicle proving establishment initiated a search for other chassis to modify. Sherman 1 and Sherman 2 tanks, ballasted to simulate the weight of the new gun, were soon brought in for testing. During an extensive 2,000-mile endurance run, the Sherman 2 suffered 38 breakdowns, including 11 major failures. It was later discovered that the necessary components simply would not fit within its rounded, cast hull. After months of dedicated effort, the British War Office made the decision on April 14, 1944, to abandon attempts to rearm the Sherman 2. Despite these significant issues, a small number of Sherman 2C tanks were still constructed. Canada, for instance, ordered 3 17-pounder turrets with the intention of mounting them on their Grizzly chassis, which was a Canadian-produced M4A1. Facing a shortage of complete turrets, Canada instead received training rigs equipped with 17-pounder guns and subsequently installed these into their tanks. At least 3 Sherman 2C tanks were completed in this manner. While it remains unclear whether the British finalized their own version, a British Army list dated June 21, 1944, does include the Sherman 2C, noting its armament of 2 7.62mm Browning machine guns. This contrasted with the Canadian Grizzly, which, like other Fireflies armed with the 17-pounder, had its hull machine gun port welded shut. The Sherman 1, when subjected to similar tests, presented fewer problems than the Sherman 2. It experienced only 22 breakdowns, with just 5 classified as serious. Its welded hull offered a distinct advantage for modifications. However, a significant limitation was its total ammunition capacity, restricted to 75 shells. A particular issue arose with the front 20-round ammunition rack, which proved unable to accommodate armor-piercing shells fitted with ballistic caps. A critical clutch part obstructed the necessary space, forcing the use of shorter shells in that particular location. The original 18-round rack located under the turret floor was ultimately replaced by 2 separate 8-round racks. This modification, however, did not significantly accelerate the loading process. Filling the ready racks, for example, took approximately 1 minute if the gun was precisely turned 40 degrees to the right. If the gun faced directly forward and the driver could assist, the process extended to about 1.5 minutes. In more challenging gun positions, this critical operation could stretch to as long as 3 minutes. Furthermore, accessing the ammunition from the racks situated beneath the turret floor necessitated exact turret positioning, a requirement that invariably slowed down the entire reloading sequence. The confined fighting area meant that spent shell casings had to be removed, Otherwise, the ammunition racks could not be refilled. Loaders were forced to throw these cases out of the turret hatch. This was because the Americans, following British requests, had begun welding the pistol ports shut on Sherman tanks. While this welding eventually stopped, many loaders still faced significant extra work. Testers even suggested removing the 14-round rack entirely and reinstating an assistant driver. This assistant could then pass shells to the loader without disturbing the primary driver. The tank's interior featured such thick paint that the ammunition rack covers would not close properly after shells were loaded. A further issue stemmed from the fighting compartment's new design. This design compelled the British to remove most of the turret lighting, leaving only a single lamp in the rear. This solitary light was not sufficient. Crew members' eyes were then forced to adjust to the dimness in order to see clearly in the front of the turret. Furthermore, the act of looking through the periscope would cause them to lose their low-light vision for several seconds. Unlike earlier tests, the gun was fired with the engine off. After just 3 shots, it became impossible to remain in the fighting area due to the absence of a fan in the turret designed to remove smoke. With normal ventilation, the tank fired 5 rounds per minute, which was the same rate as the Sherman 5C. Another recurring problem was that the muzzle brake repeatedly unscrewed itself during firing. Similar to the Sherman 5C, the turret proved to be well-balanced and easy to traverse. A full rotation required 17 seconds using powered assistance, or 1 minute and 30 seconds by hand. They also considered replacing the main gun on the M26 Pershing. Several potential solutions were examined. The simplest approach was to solely replace the gun, much like on the M10 tank destroyer. This modification would allow the tank to carry 70 shells and eliminate the vulnerable ammunition racks of the regular Pershing. Another idea was to design an entirely new turret specifically for the 17-pounder gun. A third option involved mounting the Sherman VC turret onto the Pershing chassis, utilizing the saved weight for enhanced armor protection. However, this last idea was dropped after testing at Fort Knox, as the Sherman turret simply did not fit the Pershing. To test this new tank, its turret was mounted onto an M4A3 medium tank. Americans were not impressed. The tank became too small inside, and loading its long, heavy shells proved difficult. While the 17-pounder gun could penetrate armor more effectively than the American 76mm gun, it was not to a degree that justified the significant crew discomfort. Nevertheless, Americans appreciated the design of the discarding sabot shell, subsequently utilizing it as a basis to develop their own high-velocity armor-piercing shells, known as HVAP. The 17-pounder gun's regular, powerful armor-piercing shell was not the primary advantage of the Sherman VC and EIC tanks. Their true strength lay in the APDS, or armor-piercing discarding sabot rounds. These specialized shells were fired at 3,937 feet per second and could pierce over 7.9 inches of armor at a 30-degree angle from close range. This capability was sufficient to destroy any German tank encountered up until the introduction of the formidable King Tiger. The Ordnance QF 17-pounder gun utilized these types of armor-piercing shells: AP, APC, APCBC, APCR, and APDS. Testing for the discarding sabot shell commenced in late July of 1944. Tank crews were initially confused. The gun proved unpredictable, and accuracy quickly worsened for all shell types. There were not many shells available for testing, making it difficult to isolate the root cause of the problem. By late August, testers discovered that parts of the sabot were impacting the muzzle brake, causing damage to it and consequently impairing accuracy. Widening the muzzle opening did resolve the brake issue, but it did not make the discarding sabot shell inherently more accurate. Regular shells, by contrast, demonstrated good accuracy. At 2,000 yards, shots spread by less than 54 inches, a level of precision considered sufficient for engaging a tank. Discarding sabot shells were 3 to 4 times less accurate and only truly effective from 400 yards. Hitting a Panther's turret at 400 yards was 90% likely with regular shells, but only 45% with discarding sabot rounds. At 800 yards, which was considered the maximum effective range for these shells, hit chances fell to 57% for regular rounds and 22% for sabot rounds. At 1,000 yards, the probability was 45% for regular shells and a mere 15% for sabot rounds. Another issue was that gunners could not see the tracer due to the shell's high speed, making it hard to aim. The tracer was barely visible at 1,600 yards, a range where hitting any part of a tank was almost impossible due to poor accuracy. Also, tracers often failed, with 35 out of 48 shells having non-working tracers. The British created a mixed tank. Designers successfully combined the strongest Allied anti-tank gun with a reliable chassis. However, they lost many well-known Sherman qualities, such as reliability and crew comfort. Despite this, testers at Lulworth called it one of the best we have tested recently. The war was ending, but the tank still faced tough challenges in Europe.